Okay, so yeah, welcome to our second talk today. So the talk is by Mary Hay, and it's the title is Geometry of Polynomial Shifts Loci and the Space of Trees. So please.
Yeah, thanks very much for the introduction, and thanks very much for the invitation. It's a great pleasure to see many old friends and to meet new friends here. So today I'm going to talk about polynomial shift locus and the space of trees. So I will start by telling you what is space of trees. So the space of trees is defined through a map, which is called the critical heights map. Just one sec. Okay, so critical heights map. Okay, so let's take the space of polynomials of degree d. So this is the collection of polynomials with complex coefficient of one complex parameter, and the degree of the polynomial is equal to d, which is an integer greater than or equal to 2. So let's let f be an element in poly d. That is to say, f gives us a dynamical system from the complex plane to itself. So if we take a complex number, then f will map this complex number to some number of the form a1 to z to the power of d, a to z to the power of d minus 1, and all the way to ad plus 1, where all the coefficients are complex numbers. So if we take a point in a complex plane, and we can define the escape rate function at this point. So the escape rate function is defined, well, this is basically Green's function. So this is the limit as n goes to infinity of 1 over d to the power of n of log plus of the absolute value of f to the power of n of z, where log plus is the maximum of log of z and log plus of z and 1. Okay, so basically like the escape rate function or the Green's function tells us how fast a point z in a complex plane is escaping to the point infinity under iterations of the polynomial, right? So the next player of the game is the critical set of the polynomial. So by definition, this is the collection of points in the complex plane such that the derivative of the polynomial equals 0 at those points. So basically, those are the roots of the derivative of the polynomial. And the cardinality of this set is equal to d minus 1, which means those critical points are counted with multiplicity. Okay, so now I'm gonna combine these two definitions together. So let's consider this collection. So consider the set, which is, I'm gonna consider the escape rate of all the critical points of a polynomial. Okay, so this is just a set of numbers. I'm measuring how fast each critical point is escaping to the infinity under iterations of the polynomial. And let's let hi be the I.
Sorry, Mary, yeah, to interrupt. Just a question for clarification, right? I mean, a critical point in principle could have a bounded orbit, right? I mean, then this escape rate would be 0.
Yes, exactly. You're right. So these this set could be 0, 0, 0, 0. Yes. So so hi is the ith largest number in this set. In the set defined above. Okay, so now I will write down the map. But before that, let's denote by HD the collection of d-1 tuples. Let me write T1 to T_d-1. So these are d-1 tuples of numbers such that they're ordered in non-increasing order. So T1 is the largest real number, and then T2 is the second largest, and all the way to Td-1. And this is greater than or equal to 0. Okay, so now there exists a map from poly D to HD, right? So it sends F to the tuple H1 of F, D-1 tuple, H2 of F, all the way to HD-1 of F, right? And recall, like, those HIs are the ith largest number in the set. So this is this set. So basically, like, for each polynomial, we look at the escape rate of the critical points, and we order them now increasingly, and this is the map. Okay, so it turns out that this map will descend to the moduli space of polynomials. So just recall that if I denote by MD, the moduli space of polynomials. So this is, we take the space of polynomials and considering this space up to a affine conjugacy. So basically, it's Mobius transformation fixing infinity. So we only consider the conjugacy classes up to affine conjugacy. Okay, so now the map I wrote down above will descend to a map which I call G from MD to HD, right? So it takes a conjugacy class of polynomial, and again, it maps to H1 of F, H2 of F, and to HD-1 of F. And this map is well defined since basically, like, the Green's function satisfies the following equation, right? So if we Mobius conjugate F and evaluate at this point, then the Green's levels are the same. So this this map I defined above will descend down to the moduli space, and this map is called the critical heights map. So this is the critical heights map, and as the name suggests, because this map records the heights of the critical points, critical heights map. And this map was introduced by Laura DeMarco and Kelvin-Pilgrim in around 2010. Okay, so furthermore, their main theorem, one of their main theorems, is that this map G from moduli space of polynomials to this space HD is continuous, proper, and surjective. Oh, okay, so this is their theorem, and in the 90s, so there's a theorem. So in the 90s, especially for topologists, so a theorem in topology states that, so this theorem states that a closed proper map between two Hausdorff spaces admits a monotone light decomposition. So I will define what is the monotone light decomposition. But let me just say a few words about the theorem. So in the 90s, topologists were studying decomposition of manifolds, right? So basically, if we apply this theorem to the map G, so basically like apply this theorem to the map G. So this theorem tells us this map admits a monotone light decomposition. So what does this mean? So this map admits a monotone light decomposition. So it means there exists a space. So i.e., so there exists a space which Kevin and Laura denoted by TD star, such that this map G will factor through this space. So we will have the map MD factors to TD star and to HD. So this map will factor through this space TD star such that the first map is monotone. So monotone means the fibers are connected. And the second map is light. And light means the fibers are totally disconnected. And in this case, the fibers are just discrete points. So it could be finite many points or infinite many points. Okay, so now the question is...
quick question. So essentially, sure. HD and TD star should have the same dimension in some sense? Is that right?
Yes, exactly, right. Yes, so basically, right. So the mystery is this TD star, because this TD star, we can, if you go through the proof of this theorem, so TD star, how do we prove there exists a space TD star, right? So the proof tells us TD star is constructed by collapsing connected components of fibers of this map into points. So basically, I take the map G, and for each point in HD, I look at the fiber, and I collapse each connected component of the fiber into points. That's how I construct TD star. So for one hand, the space TD star is defined. We know what it is from this construction in topology. But on the other hand, we want to understand what it means dynamically. So because it's a space which is in between, so this space is called space of trees. So in some sense, it encodes the dynamics of the polynomials and also the topology of the moduli space of polynomials. So we want to understand what it means dynamically for this, how to understand this space TD star dynamically. Okay, so now I want to tell you what is the shift locus. So shift locus of degree D is a subset of the modular space of polynomials. So these are conjugacy classes in MD such that all the critical points, let me just write HI of F. So all the critical points of the polynomial converges to infinity under iterations of the polynomial. So all the critical heights are positive. So this is, or the smallest one is positive. Okay, so when D equals 2, right? So the shift locus in degree 2 is simply the complement of the Mandelbrot set. So as Alex just told us, so when D equals 2 for quadratic polynomials, we only have one critical point. So either the critical point goes to infinity under iterations of the polynomial or it does not. So if it does not, then this polynomial lies in the Mandelbrot set. So the shift locus is the complement of the Mandelbrot set. And we know what is the homotopy type of the shift locus when D equals 2. So S2 is homotopy equivalent to the circle, since the Mandelbrot set is connected by duality-Hubbard. And when D is greater than √2, 3, we can ask the same question. So S3 is, SD turns out to be much more complicated. So what is the topology of SD? Okay, so the study of topological properties of this subset of the modular space started from Blanchard, Devaney, King. Where they proved that the fundamental group of this shift locus when D is greater than √2, 3 is infinitely generated. So that is to say, when D is not equal to 2, this is a huge space. And this space has very complicated topology. And Laura DeMarco and Kevin Pilgrim also studied the shift locus when D is greater than √2, 3, and in particular, they wrote 5 papers. So for some of for some of the talk, we're citing results from one of their papers. And the third development was the recent development of Danny Caligari, where he gave an algebra geometric description of the topology of the shift locus. So in this talk, we're not going to explore the topology of the shift locus, but on the other hand, we're going to explore the geometry of the shift locus. So we want to give a geometry. So in particular, we define a geometry on the shift locus such that it will tell us to understand, we can understand the space. Let me just write STD star. Okay, so what is STD star? Well, there's only one more letter than this TD star. So remember, like TD star is the space that is in between MD and HD, right? So now, if we look at the shift locus, so shift locus is the subspace where all the critical heights are strictly positive, right? And I can look at what is the fiber of this SHD. So this is the space STD star. So basically, like we want to understand the space of trees where it corresponds to the shift locus. So this is where the space is.
So quick question. I mean, can one think about these spaces without the S as some kind of compactification of the spaces within S? I mean, certainly this HD is some kind of a compactification or a completion of a SHD, right?
Yes, yes. So SHD is dense in HD.
Yeah, okay. All
right. Right. Yes. So I think you are getting the point. So basically, like we want to, so there, let me just write down the theorem. So the theorem is, we want to say like this STD star, this space of trees, is lying in the compactification of the modular space. Okay, so this is our main theorem. So there exists a distance function rho d on the shift locus such that the metric space SD rho d is complete if and only if D is equal to 2, and if D is greater than or equal to 3, so the metric space is not complete, and there exists a subset, I call it X, which can be exclusively described there exists a subset X in the metric completion which I call SD hat, such that X is homeomorphic to the space. Let me just write PSTD star. So basically, like PSTD star is one more letter than STD star. This just means in this space, the critical heights are normalized. So the largest critical height is equal to 1. Okay, so basically, like we mod out by stretching, by just like increasing the critical heights. Okay, so basically our main results provides a way to understand what is STD star. So basically, like we think of it as lying in the boundary of the shift locus with respect to this particular geometry that we put on the space. Questions?
Yeah, I'm not sure whether I understand. Is there some kind of cartoon picture that you can draw just to illustrate how these spaces are related to each other?
Okay, so basically the mystery is, so if we start with this say like shift locus, right, and then we kind of like understand there's a mystery space called STD star, and there's HD, and the purpose is to understand what is STD star. So basically we want to say, we want to put a metric on the shift locus so that the shift locus becomes a metric space, and this metric space is not complete, and in the completion, so basically like kind of like boundary at infinity, we can find a subset which is this STD star. So basically, like this gives a way to understand STD star, which is basically you take a sequence, like it's a collection of equivalence classes of Cauchy sequences in ST, and this is how we would understand this STD star. Okay, so for the rest of the talk, I will tell you like what is our construction of this distance function. So in particular, this distance function, it has to be dynamical, which means it's invariant under conjugation, and it records basically, since we want to interpret STD star as the boundary of the shift locus, then this metric will encode the information as we go to the boundary. So basically, like we have a Cauchy sequence of polynomials in the shift locus, and we want to record what is the information, dynamical information of this sequence. Okay, so so part 2. So to start the construction, I want to switch gear because our metric comes from a total different field of mathematics. So our metric comes from geometric topology, in particular moduli space of metric graphs. So this is a subset of the outer space. So metric graphs, or if people know what is an outer space, so geometric group theorists use outer spaces to study something called out FN, so the outer automorphisms of the free group generated by n generators. So okay, so what is the metric? What is the modular space of metric graphs? So let's first start with connected finite graph. And graph. And in our application, we will just take rows graphs of 2D minus 2 petals. So actually, we will only consider one graph, but the theory of modular space of metric graphs is general. Okay, so a length function.
So sorry, what is a rose graph? I mean, a bouquet of circles?
Okay, so this is just like a graph with only one vertex and 2D minus 2 edges. So,
yes, so
this is
a bouquet of circles, right?
Yeah. Yes. It's just a bouquet of circles. So 2D minus 2. So this is the only graph that we will consider. Okay, so a length function is a function L from the edge set of the graph to strictly positive real numbers. So a length function just assigns a positive real number to each edge. And a graph together with a length function is a metric graph. Right, so you should think of the graph as some kind of like topological one-dimensional manifold. And if we put a length function on it, it's a geometry on the graph. It specifies how long is every edge, right? So a graph together with the length function is a metric graph. It's a geometric object. So if we have a metric graph, or if we have a length function, we can define what is the entropy of the length function. So the entropy H gamma of L of a length function L is defined as the limit as t goes to infinity. So this is kind of like the topological entropy that people have already seen. So 1 over t log of number of loops in the graph, such that the length of the loop is smaller than or equal to t. So this collection is a collection of circuits or loops in gamma, which means it's a sequence of edges. So that the tail of the last edge equals the starting point of the first edge, and every edge is not the inverse of its adjacent edge. So basically, like you cannot go like this and then come back like this, right? And then basically we count how many loops are there in the graph up to length t, and take log of this number and divide it by t and take the limit as t goes to infinity. So this is very much similar as the entropy for geodesic flows. Okay, so now if I denote by m gamma the collection of length functions on gamma. So you can think of this as basically like a Teichner space on gamma. So the graph is something topological, and then now I want to put all the geometries on gamma. So now I obtain an entropy function on this space m gamma. So this is a function from m gamma to R, where I take a length function and map it to its entropy. And I think it's just greater than or equal to 0. And then for this entropy function, there's a theorem due to AL gap, Clay, and Rick. So these people study outer spaces and out FN. And what they proved was the entropy function this H gamma from M gamma to R greater than or equal to 0 is real analytic and strictly convex. So I should say where is this real analytic structure comes from. Okay, so so for M gamma, we should think of M gamma as a subspace inside R to the cardinality of E, right? Because for every length function, we get E number of, so the number of edge numbers, and then we should think of this length functions on gamma as a subspace of R to the power of E. So in this case, because these are subsets of Euclidean spaces, then we can talk about what is the differentiable structure and what it means for this function to be real analytic and strictly convex.
So
okay, so now...
Wait.
Yeah.
Not so fast. Quick question. For your Rose graphs, I mean, you should be able to say explicitly what the entropy function is, no?
Yeah, exactly, right. So it's complicated, but there is a formula to write it down.
Oh, it's complicated? Oh, okay. Well,
yep. Because the weight is not 1, 1, 1, 1. I think if you put 1, 1, 1, then it's simple, right? Yes. So, right. So, but it is true, like there's a closed form formula for the Rose graph. What is the entropy function? Okay, so now we want to normalize a little bit. So we want to consider M gamma 1. Okay, so what is the space? So this is space of length functions on gamma such that the entropy of this length function is equal to 1. And so for, if I pick a point in this M gamma 1, and what I'm gonna do is I'm gonna build a inner product. Well, actually, like these people, they built an inner product on the tangent space of M gamma 1 at this point. So the tangent space, first, we need to compute what is the tangent space. This tangent space is the collection of vectors in the Euclidean space, such that the Euclidean inner product of this vector with the gradient of the entropy function at this point is equal to 0. So this is the Euclidean inner product. Okay, so and then we can define an inner product on the tangent space. So if I take two vectors in the tangent space, then I define their inner product to be the Euclidean. Okay, so let me just write H gamma, this inner product, as the Hessian of this entropy function. So basically, the inner product is given by the Hessian of this function, of this entropy function. Okay, so this is an inner product on the tangent space. Okay, and here this H is a Hessian because the entropy function is strictly convex, so the Hessian is non-degenerate, and this defines a inner product on the tangent space. Okay, so now we're basically gonna use this inner product to define a metric on the shift locus. So back to shift locus. So how do we relate shift locus to this M gamma 1? And we can basically use this inner product to define what is the length of each tangent vector. Okay, so let's start with generic points in the shift locus and metric graphs. So we're gonna relate generic points in the shift locus to metric graphs. Okay, so let me first define what is generic points. So a generic point in HD, remember HD is the d-1 tuples of real numbers. So a point is generic if, let me just erase this. So Ti to the power of n is not equal to Tj of power m for any n m greater than or equal to 1, and for any ij between 1 to d-1. So any pair of entries in HD does not share a common power. So that's what generic means. And a generic point in SD means that the critical heights of this polynomial, any pair of critical heights do not share a power. So for any n m greater than or equal to 1, and for ij from 1 to d-1. Okay, so at generic points, the critical heights map is very nice. So this is again a theorem of Laura and Kevin, so DeMarco-Pilgrim. What they prove was the fiber of G from this modular space to HD at any generic point in HD is a finite disjoint union of smooth d-1 dimensional tori, each component of which coincides with a twist deformation orbit. Okay, so I haven't said what is twist deformation orbit, but twist deformation orbit comes from Brenner. So it is the same twist deformation as Brenner-Hubbard ring motion. So intuitively, these motions are such that you can deform a polynomial by kind of like twist the critical points of the polynomial, or you can something called stretching. You can stretch the critical points, which means you can increase the escape rate of every critical points. So what is the consequence? Well, the statement of this theorem is very long, but let me just give you a simplified version of what the theorem is saying. So this theorem is basically saying that if we take a generic point in the shift locus, generic, and we look at the tangent space of this at this point of the shift locus, so this tangent space will split into two parts. So one part is spanned by this twist deformation. So we'll write as twist twist F0. And there's another part which I will just write HF0. So this is a subspace that is spanned by stretching. So basically you can stretch the height. So H stands for stretching the heights, and twist means you can twist the angles. So basically, like if you think about the location of the critical points, right? The critical points lies in the complex plane, and you can either stretch its heights, which means make it goes to the point infinity faster under iterations of the polynomial, or you can kind of like twist it around on the same Green's level. Okay, so basically like Laura and Kevin's theorem tells us there's a splitting of the tangent space into these two parts. And so now, what do we want to do? So we want to, so let me just draw you a cartoon picture. So I want to define a metric on the space SD, right? So that is to say, I take 2 points, F1 and F2, in the shift locus, and I want to tell you what is the distance, right? So what is this distance between F1 and F2? So this distance, as in calculus, so you draw a path between F1 and F2, right? So in calculus, what we learned is I just integrate, say from 0 to 1, and I parameterize this path, and I take the tangent vector, right? So basically this is gamma t, and for every t, I have a tangent vector along the curve, and I'm basically integrating the length of the tangent vector. So, but this length of the tangent vector is something that I want to define now. So basically, like, it depends on how you define this length of the tangent vector. And the length of the tangent vector is defined as follows. So basically, we are going to use the inner product on this space M gamma 1. Okay, so how does this work? So let me just draw you another picture. So here is SD, right? I take a point, generic point, and I look at its tangent space. So suppose I take a tangent vector. This is V, right? So I can represent this tangent vector by a path, a smooth path in my space. Say I call this maybe FT. Okay, so maybe gamma T. Okay, so, and now for each T, I'm gonna associate to each T a point in M gamma 1. Okay, so that for this curve gamma T, I obtain a curve in M gamma 1 with say like this is LT, right? So, and this point is L0. So that this vector V is mapped to the vector tangent here, right? And remember, we have an inner product on M gamma 1. So I know what is this tangent vector. So let me just call this map iota F0, right? So this tangent vector is iota F0 of this V, right? So because I know the inner product on M gamma 1, I know how long this iota F0 of V is, and then I just define the length of V. Okay, so I just define length of V to be this length of iota F0 of V as this H gamma in the space of M gamma 1. But I haven't told you how to construct this path LT. So that's the key point. Okay, so let's slightly go back to here. So so this depends on where V is, right? So from the theorem of DeMarco-Pilgrim, there are 2 cases for V. So if V lies inside this twist, maybe let me first state, not in the twist component. So what does this mean? So this means I look at this gamma T inside my shift locus, so this path, gamma T. So along this path, all the critical heights are going to change, right? Because this tangent vector V is not in the twist component. So if this is the case, I'm gonna define this path LT as follows. So actually this is L hat T because it's in the M gamma 1. So I will first define LT. So for every T in -1 to 1, so we want to define a length function, right? So so this is a length function on this edge of this bouquet of D minus 2D circles, 2D minus 2, right? Strictly bigger than 0. Okay, so how do I define it? So I define L sub T of E sub J to be H1 of T. So for every T, I have a polynomial, a class of polynomials. I look at what is the H1 of this polynomial, right? And so this is when j equals 1, and when j equals 2 to d minus 1. Okay, so let me just write it down and explain what these formulas are. So j is 2 to d minus 1, and the rest is 1. So j is equal to d to d minus 2. Okay, so this formula means if the vector v is not in the twist component, which means along this path gamma t inside my shift locus, if I move t, right, so the polynomials are going to change, and they, in particular, all the critical heights are changing. So I'm recording, so I have a bouquet of 2d minus 2 circles. So for the first d minus 1 circles, I'm going to record how the critical heights are changing. And in this case, because the heights are changing, so for the last d minus 1 circles, I'm going to assign the number constant 1. So the last d minus 1 numbers are meant for the change in the twist parameter. So but now, because the heights are always changing, so I just record heights, and I keep 1, which is a constant, for the twist parameters. Okay, so the second case, if v is in the twist component, which means if I draw a smooth path in the shift locus representing this vector v, then along this path of polynomials, all the critical heights are gonna stay constant, but the twist parameter are gonna change. So it's like you have critical points. The critical points are kind of like winding around all the level sets of Green's functions, but the critical heights are going to stay. So in this case, I still have 2d minus 2 bouquet of circles, a bouquet of 2d minus 2 circles. For the first d minus 1, right, I'm always going to use these numbers to record what is the change in the height. And for the last d minus 1, I'm going to use these coordinates to record what is the change in the twist. So in this case, the formula looks a little bit different. So the heights are still the same, but since the heights are all constant, so in fact, the first d minus 1 coordinates are constant, and the last d minus 1 coordinates will be something that looks like this, minus d minus 1 of t, and divided by, so there's a normalization of hd, and this is when j equals d to 2d minus 2. Okay, so let me just say what is theta j minus d minus 1 of t. So this is basically like recording how twists are changing up to a normalization. So, and this normalization is given in the paper of Laura DeMarco and Kevin Pilgrim to make the technical details will work out. Okay, so normalized twist. Okay, and then ht is defined as the maximum of h1 of t, or 1 over hd minus 1 of t. So you either take the largest or 1 over the smallest, and you compare which one is larger, and you normalize by this factor. Okay, so well, the definition is chosen so that like our construction will work, and in particular, well, like so basically, like yes, so this factor is designed so that like we will prove the completion contains this STD star. Okay, so it's a little bit artificial to put this HT, but that's the only way that we can put the space into the completion. Okay, so now I have defined LT, right? So now if I normalize this LT, so LT hat is basically, I multiply the entropy of LT to LT, right? So this LT hat is an element. So for every T, I do this normalization, then I will obtain an element in M gamma 1. So this is how I construct. Okay, so let me just draw the picture again. So this is how I construct a path in M gamma 1 corresponding to a path in SD representing a vector at a generic point. So I have a path gamma T here. So gamma 0 equals F0, and I take the derivative as 0. This is equal to this V. And then under this map, I obtain a path L hat T inside M gamma 1. And then so at L0, I obtain this vector. So this vector V gets mapped to this vector. So I denote this map by iota F0. Okay, so that's basically how we construct the metric. So basically I define the length of the vector in the shift locus to be the length of the vector under this map iota. And then this, because this map lives in M gamma 1, so this is going to be the length with respect to the entropy, the Hessian of the entropy function that we discussed earlier. Okay, so this is okay, so this is basically like how we define the length of the vector, and then how we define the distance function. So this distance function is defined as follows. Okay, so we take F1 and F2, and this pair is sent to inf of gamma. So where gamma is piecewise generic curve connecting F1 to F2. So basically, like we first prove for any 2 points F1 and F2 in SD, they can be connected by generic piecewise generic curves, and then we calculate what is the length of each curve, and you take the infimum, and this is the definition of this function. So this is gamma j prime of t, and this tangent vector is has length SD, which is defined above, and we integrate dt. And then basically we need to prove that this function defined above is a distance function, which means it satisfies triangle inequality, and the distance is greater than or equal to 0 and equal to 0 if and only if the 2 points are the same, and also it satisfies the symmetry. So the distance between F1 and F2 equals F2 and F1. So so this is or a distance function or a metric, so that this shift locus together with this metric becomes a metric space, and then metric space, and then the more detailed work is about the study of Cauchy sequences in this metric space, and we prove the metric space is complete when if and only if when d equals 2, and when d is greater than or equal to 3, this metric space is not complete. And because it's not complete, so in the completion, in this boundary at infinity, there's a subset which we can describe, and this subset is homeomorphic to PSTD star, which is the space that is given by Laura and Kevin, but defined through some abstract from abstract theorem in topology. Okay, so I think I will stop here, and thank you very much for your attention.
Yeah, thanks. Thanks a lot. Let's thank our speaker. And let me start the discussion. Are there comments or questions? So let me ask a question. Is there some kind of formal analogy of your metric with, let's say, the Weil-Petersen metric on Teichmüller space? I mean, it looks a little bit like it, right? Because there you also have...
Yeah. So this is, okay, so on M gamma 1, the metric I wrote down by the work of Aelgab, Clay, and Rick, these are Weil-Petersen metric. So this metric is Weil-Petersen metric. This one, right? So this inner product is the pressure metric or the Weil-Petersen metric. Because, okay, so metric. So there's another formalism given by Polycott and Sharp. And they also defined Weil-Petersen metric. And their metric is exactly the same as the metric of Aelgab, Clay, and Rick. The problem is on our space, on the shift locus, it is not a Weil-Petersen metric because this is not an inner product. Because if we look at how we defined these vectors, because the vector, if we take a vector in the twist component and we take another vector in the non-twist component, we cannot add them. Like, we don't know how to define addition. So that's why in our space, it's not a metric, but it gives a length of the vector. So we can define a distance function.
I see. So it's just a Finsler type metric.
Yeah, exactly. Right.
Okay. Are there other comments or questions?
I have one, Mary.
Yeah.
So you and Hongming define in another paper pressure metric on its hyperbolic component.
Right.
So can you compare these two metrics?
So the problem is for that one, that metric is not defined on the shift locus because shift locus has parameters where all the multipliers are real. So you can take a real polynomial in the shift locus. So for those tangent spaces, those metrics are not defined. Yes, so like we cannot use the metric defined in another paper to do this construction. Yeah, because we have a assumption in the main theorem where we require the multipliers to be not. There exists a multiplier which is not a real number.
Right. So for this metric graph, is there any thermodynamic formalism so that we can think of this entropy as a pressure function? Or...
Yes. So right. So this is in fact contained in this paper of Aelgab, Clay, and Rick, and also Polycott and Sharp. So basically if you read Polycott and Sharp's paper, it's still you can consider what is the pressure, and it's basically the same as the pressure metric.
So yes, they on this dynamical systems on the boundary of something.
It's still yes. So if you have a graph, then that gives you kind of a symbolic dynamical systems, right? And then they started from there. And then you can define what is pressure, and you define what is pressure metric. It turns out these two guys are the same.